All right. Hi, everyone. Welcome to the MQC seminar between University of Michigan, Michigan State, and Purdue. Today, we're very happy to have Sohaib Alam from NASA and USRA to talk about dynamical logical qubits and the Bacon-Shor code. So, Sohaib, take it away.
Thanks, Ryan. Very happy to be here, and thanks for having me. So yes, as Ryan said, today I'll be talking about dynamical logical qubits and the Bacon-Shor code, or you could think of it as Floquet Bacon-Shor codes as well, which is work I did with Eleanor Riaphil at NASA, and we just recently put out this paper. And I should say that this work really grew out of conversations that both Eleanor and I were having with Ryan back in the day, when we kind of all got interested in Floquet codes, which at the time seemed like a very novel and very different, type of error correcting code families. And Eleanor asked us this question about, could you put a Floquet code, or could you construct a Floquet code on a square lattice? And I think it was a stunningly simple question, but one that evaded a clear answer for quite a long time. So it was a long string of investigations that ultimately led to this paper. So very happy and excited to share this. So my talk today, and I should apologize in advance, like I had to sort of scramble together a few slides. And as I was telling Ryan, I'm out in the wilderness at the moment. I wasn't really supposed to be doing anything work-wise, but I couldn't turn down the offer when Ryan said if I could give a talk. So please interrupt me at any time with questions. Tell me if I'm going too slow or too fast or anything like that. But what I had in mind for today was just giving a review of stabilizer and subsystem codes, mostly kind of establishing notation that I would use in, our construction of this Floquet Bacon-Shor codes. I will give an overview of Floquet codes, of course. Mostly, I will be discussing just the very first example of a Floquet code. There have since been several examples, many of which I find quite interesting and illuminating, but, in the interest of time, I think we'll have to limit ourselves to that first example. And then, we'll discuss the Floquet Bacon-Shor construction. That is the main, topic today, I guess. And I'll finally conclude with some open questions and some next steps. Okay, so just to give a brief review of stabilizer or subspace codes, I like to start off with the simplest example that I could think of, which is the 3-qubit repetition code, which is just like a quantum version of the classical repetition code. So you identify your logical zeros and ones as just bit strings of, the all zeros bit string and the all ones bit string. And this particular code can correct, for example, a single qubit error on the leftmost qubit, which, I'm just calling this is the first qubit. And we do so by measuring the parities between neighboring qubits. So if I measure the product of Z on the first and second qubits, as well as the product of Z's on the second and third qubits, their measured values will reveal to me that, if under the assumption that only single qubit X errors ever happen, then under that assumption, this measurement result tells me that there's a single qubit X error on the leftmost qubit. And so I've identified that qubit, and now I can correct it and bring it back to the code space. Now, this particular code encodes one logical qubit, and so the state of that logical qubit I can write generally as some superposition of the logical code words, and I can identify, particular logical operators for those code words too. So you can check, for example, that this identification of the logical X and Z's satisfy, the properties that you would want. So for example, it would convert the X operator would convert the logical 0 to a logical 1 and vice versa, whereas the logical zeros and ones are respectively the +1 and -1 eigenstates of the logical Z operators. And an important but crucial point about these logical operators is that they commute with, but they cannot be generated by the stabilizer checks that we mentioned just now, the Z1, Z2, and the Z2, Z3. Okay, so somewhat more abstractly, we identify a stabilizer group as a subgroup of, as an abelian subgroup of the poly group, right? So Z1, Z2, of course, trivially commutes with Z2, Z3 because both of these were just, composed of Z operators. And so one particular way to express that fact is to employ this so-called virtual qubit basis. And this is something that's basically it's all I used in the construction of the flow gate code eventually. So it's important. And the idea is that, so A, because these stabilizer generators are commuting, I can basically write them as like, so the main idea is that instead of writing operators in terms of physical qubits, identify these collective degrees of freedom that I call virtual qubits. It's really kind of an automorphism of the poly group that sort of satisfies and maintains the usual commutation relations. That is to say, like, operators on disjoint sets of qubits, they will trivially commute, but then X and Z operators on the same qubit will anti-commute and so forth. And so in terms of these, basically, I'm saying like, okay, the first two qubits are my stabilizer qubits, and their Z operators are precisely the stabilizer generators, right? So Z1 and Z2, I now, I just put bars on top of them to denote that these are virtual or qubits or collective degrees of freedom. The logical qubit, I'm just calling it like the third qubit without loss of generality. And these are just, the logical X and Z's operators that we identified previously. And of course, together with these Z operators, you can also write down some X operators that will, give you the usual, that will, give you the required commutation relations. And these really generate the detectable errors of your code, so to speak. You can, of course, move back to the physical qubit basis as well, right? So like the physical Z1 operator in, and the physical Z2 operators, et cetera, you can write all of them in terms of these virtual qubit operators. The interesting thing in this case, in the 3-qubit repetition code, is that because it can't detect any phase errors, all of these, in fact, are logical errors, right? Because so the logical operator is just like a Z, physical Z on any one of those 3 qubits. But it can detect and correct single qubit X errors. So for example, X1, is the product of these virtual X1 and X3 operators. So recall over here that we're calling these first 2 qubits the stabilizer qubits, right? So if I have a factor of X1, it means it only flips that first stabilizer check. If I have a factor of X2, it means it flips, the second stabilizer check. And so if I have an error on the leftmost qubit, which is X1, it will only flip that leftmost stabilizer check. If I have an X error on the middle qubit, it will flip both of those stabilizer checks. And finally, if I have an X error on the rightmost qubit, it will only flip that rightmost stabilizer check. And so in this way, I can, completely isolate and identify, under the assumption that only single qubit X errors ever happen, I can distinguish what those errors are through the pattern of the stabilizer checks or their measured values, which we call syndromes, right? Okay. So essentially, then what we're saying is that here's a stabilizer group. It's some abelian subgroup of the poly group. These are its stabilizer generators. And what we've done is essentially identified, so let's say that we had some stabilizer that was generated by R such independent operators. And we're saying that those R operators are the logical Z operators of some virtual qubits that we call the stabilizer qubits, right? And our usual definition of a stabilizer code space being the +1 eigenspace of these stabilizer generators translates to the statement that essentially in this virtual qubit basis, your first R qubits, which we've identified as a stabilizer qubits, are all set to 0, right? Because 0 is the +1 eigenstate of Z. And the same thing kind of goes as before, which is that like once you fix any poly operator, you've sort of divided your Hilbert space into 2, into the +1 and the -1 eigenspaces. And so if you fix R many independent Pauli operators, then you've done that division R many times. And so the dimension of the space that you end up with is like 2 to the n minus R. So in other words, you end up with n minus R remaining degrees of freedom. And those degrees of freedom are precisely your logical qubit degrees of freedom. And you can also, oftentimes you'll see this kind of statement that your Hilbert space, in the case of stabilizer codes, is split up into this direct sum space where you have the code space and then, direct summed with everything that's not in the code space. I think that in this virtual qubit picture, it becomes a lot more clear, right? Because this code space is really the part of Hilbert space that corresponds to these first R stabilizer qubits being in the zero state. And then as soon as one or more of these stabilizer qubits flips to the one state, that's when you've sort of moved away from the code space, and you could hopefully detect them and correct them and bring it back to bring those stabilizer qubits to be in the zero space, in which case you're back into the encoded space. Okay. So finally, we must also identify the logical operators of subspace or stabilizer codes. And we already said that these first R generators, we're calling these the Z operators of some stabilizer qubits. Now, the logical operators live in the normalizer of this stabilizer. And the normalizer of the stabilizer is defined as the subgroup of the Pauli group that commutes with every element of the stabilizer. Now, I should mention that, strictly speaking, what I actually just said is the definition of the centralizer. In the case of the normalizer, the definition is that you can conjugate every element in this group and get some other element in the group. But in the case of Pauli operators, things either commute or anti-commute. So these definitions coincide, at least in the case of stabilizer codes. In the case of subsystem codes, I'll actually be using centralizer. But in this case, they're both the same thing. You should just think of it as like set of all operators that commute with every element in the stabilizer. So again, I think that in this virtual qubit picture, it's kind of nice and neat to look at, to be much more intuitive, because clearly if I have an operator on some other qubit, regardless of whether it's an X or a Z, it's going to commute with, any operator in the first R qubits, right? So those things are all in the normalizer. That is to say, they commute with these operators, but they're also not in the stabilizer, right? And that's where your logical operators live. The detectable errors are given by everything in the Pauli group that's not in this normalizer. So everything that's not in this group is going to contain factors of the X operators of these first R qubits, right? Because that's all you have. The only thing we're really missing here are those X operators. But of course, you could have something like X1 times Z2 or something, right? Primes. But the point is that those detectable errors are going to anti-commute with one of these Z's. And so that's going to, produce some kind of a non-trivial syndrome. And yeah, but they're always going to contain one of those factors. Okay. So that's all I wanted to say about stabilizer codes. If there are any questions, please stop me. But otherwise, I will continue to say that with subsystem codes, we sort of, generalize subspace codes in the following way. So in the case of subspace or stabilizer codes, we said that our Hilbert space splits up into this direct sum of the code space plus, stuff that's basically perpendicular to the code space. In the case of subsystem codes, what we're really saying is that that code space is further split up into a tensor product structure. And the idea is that we identify an equivalence class of code states to say that, as long as you don't disturb this subsystem A of the code space, you can do whatever you want on subsystem B and still have the same logical information. And so the way that you enforce this equivalence class is basically through multiplication of some, generically non-abelian subgroup. And this is all very abstract, but you'll see an explicit example, and we'll really dig into it. And hopefully you'll get a taste of why this is cool, or this is important in the first place. But just to complete some terminology, in the case of these subsystem codes, we're very naturally led to this notion of a gauge group, which enforces this kind of equivalence of code states. This gauge group is a non-abelian subgroup of the poly group, unlike stabilizer codes, right? Where we had a stabilizer group, which was an abelian group. But the center of this gauge group, the center of any group is defined as like, the subgroup of that group, which commutes with every element in that group, right? So the part of this gauge group that commutes with everything in the gauge group is what we identify as the stabilizer group. And so, again, employing this kind of virtual qubit notation, what we can say is that this gauge group G is generated by, well, some stabilizer generators, which, again, we're repackaging into these virtual qubit degrees of freedom. And so we're saying, like, there's R many stabilizer generators, and everything else, you can show that they can come packaged in these kind of, pairs of operators that must, again, satisfy those usual commutation relations. And those are precisely your gauge degrees of freedom. And the fact that you get both X and Z's for those degrees of freedom is exactly what's telling you that those qubits, so like, these, your first R qubits are the stabilizer qubits, and these remaining K qubits, those are your gauge qubits, and they could be in whatever state you want them to be. But those first R qubits really have to be in the 0 state, or, so to speak, like those have to be in the +1 eigenspace of the center of the gauge group, which is the stabilizer group. And so finally, now everything else, so if you have like n many physical qubits, and you do this kind of decomposition of the gauge group, then basically n minus r minus k many degrees of freedom, those are, how many logical qubits you end up getting. So, okay, that's a lot of formalism. So let's put that into practice, right? So the explicit example, and to me, probably like the simplest example of a subsystem code, is the Bacon-Shor code. Now here, the gauge group is generated by two-body checks. And this is one of the attractive things about subsystem codes in general, is that, so I didn't, previously I mentioned all this like formalism about like, okay, here's a gauge group, it's a non-abelian group, etc. But you might wonder, well, why do we need a gauge group in the first place, right? And the idea roughly is that measuring stabilizer check operators can be difficult or, fault prone, right? So if you want to do everything fault tolerantly, you want to make the weights of the operators that you actually measure as small as possible. And so the advantage, the generic advantage that you get with subsystem codes is that what you measure are really the checks or the generating operators of the gauge group. And then you can multiply the operators of, those measure checks to infer the value of some higher weight stabilizers. And so in this way, so this is maybe like we'll see exactly how this works in the case of the Bacon-Shor code just now. So in this case, the gauge group is generated by these two-body check operators. We have horizontal XX operators between every nearest neighbor pair. So you'll have like X1, X2, X2, X3, X4, X5, etc. Right? And then you also have vertical ZZ checks between neighboring qubits. So Z1, Z4, Z2, Z5, etc. Now, these clearly anti-commute with one another generally, right? Because X1, X2 anti-commutes with both Z1, Z4, and Z2, Z5, right? And so this is a non-abelian group, right? But there is um, a center of this gauge group. It's a non-trivial center, and that includes the stabilizers of this code. So there's vertical X stabilizers that are given by the product of the horizontal X checks. So if I multiply, at this particular X check, X7, X8, X4, X5, X1, X2, then that product gives me an X stabilizer. And you can sort of convince yourself that this will commute with every ZZ check, right? Because it will meet every ZZ check at precisely 2 qubits. And so it commutes with all ZZ checks. It, of course, commutes with all the X checks trivially. And so you have, one X stabilizer per column of square plaquettes. And likewise, you have Z stabilizers per row of square plaquettes, right? So each of these Z stabilizers, which again, in this case is given by the product of, this vertical ZZ check, this one, and this one, this will commute with any of the XX checks, right? Finally, we have the logical X and Z operators, and this is just given by a product of Z's along any row, right? I've drawn it on the topmost row, but really it could be any one. And the product of X's along any particular column. And the reason why they're logical is because you can, again, see that, for example, each of these operators will commute with all the checks, right? So in this case, it trivially commutes with ZZ checks, but it will also meet any XX check at precisely an even number of qubits, right? And so this one commutes with all the gauge group elements, but it's also not part of the gauge group, importantly, right? That is to say, like, you can never multiply any gauge group elements to produce these two operators. And so these are your logical operators. And in the case of the Bacon-Shor code, no matter how large you make the lattice, you'll always encode one single qubit, right? Okay. And we described, and so, okay, so like, the point of doing things in this way, and by the way, like, why do people call it Bacon-Shor and not just Bacon code, even though it was just Dave Bacon, as far as I can tell, who came up with this? It's because this minimal 3x3 lattice example is actually kind of equivalent to the 9-qubit Shor code. But in the case of the 9-qubit Shor code, you really have to measure weight 6 stabilizers. The advantage that you get doing things in this way is that you can split up that measurement into, 3 measurements of like 2 qubit operators, right? And then like what you really have to measure are these like XX checks, which is much simpler to accomplish. And then you just multiply those measurements together to form these stabilizers. So that's the main advantage. We previously talked about this kind of like, virtual qubit notation. This is from one of my notes from back in the day, and I left it here just to impress upon you that this is not what I ultimately used, but just to show you that, there's not just one choice for how you transform things into virtual qubit operators. Of course, your stabilizers are fixed, right? So you know what the stabilizers are in this case. Like we said, they're like weight 6 operators, like given by these letters, etc. So we know what Z1, Z2, Z3, and Z4 are. We can even make a choice of what Z9 and X9 are, right? Like, I mean, just by fixing the column and the row on which those operators are defined. But there's actually a lot of freedom in how you get to define these X operators for the stabilizer qubits, as well as like the remaining gauge degrees of freedom. And later in the talk, you'll get to see like another choice, which is particularly convenient for flokifying this Bacon-Shor code. But one quick thing I'll mention over here is that, like, just as before, you can also work your way the other way. You can work your way backwards and figure out what the reverse transformation has to be. The nice thing about the Bacon-Shor code is that, so remember that, the first 4 qubits are the stabilizer qubits. So if I pick, for example, let me just look at the bottommost row, right? So if I have an error on, so in my notation, if I just go back here, qubit 7, 8, 9 are the qubits in the bottommost row. So an X error on any one of these qubits is going to contain a factor of x4 prime, which means that in my notation, I'm calling this particular Z operator, which is this Z stabilizer. So it's going to flip the Z stabilizer, right? And so that's the only non-trivial factor that it contains. Everything else, like x6 prime, x8 prime, those are just gauge degrees of freedom. So in other words, whether I have an error on this qubit, or this qubit, the correction operation is to then apply an X operator on any one of these qubits. And then, the correcting operator times the actual error is just going to give me some operator that's in the gauge group. And so I'm back into the code space again. I might have done something non-trivial to the gauge qubits, but, I restored the state of the stabilizer qubits, so to speak. Okay. So yeah, so that's all I wanted to say about I could go, if you've been paying attention to the slides, you might see this like exclamation mark over here about this factor of logical qubits. Let me just say very quickly that that's basically not an issue, even though it might seem like one, written in this basis. The point that I'm trying to alert you guys over here is that basically, apart from this factor of x3, which flips one of these stabilizers, in this case it's going to be this upper Z stabilizer, we also have a factor of x9s. But those factors of x9s are common to every physical qubit in the topmost row. So in other words, and everything else, the x5, z1, z2, are either gauge operators or they're stabilizer operators. So the point is that once I've identified, that there's some physical qubits, some physical X error on the topmost row, then I can apply a correcting X operator to any one of those qubits in the topmost row, and it will cancel off not only this X3, but it will also cancel off this X9 error. So in fact, you're left with no logical error, even though it might seem temporarily that you've done something, you've messed up, your logical information or something. Okay, so with that, I think we're roughly at halfway time, and I'm going to spend the rest of my time talking about flow K codes. So if there's any questions about, anything we said about stabilizer or subsystem codes, please let me know. We can also, of course, always go back and discuss more if needed. Okay. If there are none, and like I said, please feel free to stop me for anything that for any question that might come up in your head later too about something. But okay, so we discussed what stabilizer codes are. We said what subsystem codes are. Now I'd like to talk about flow K codes. And the history of the flow K codes is something, the reason why I spent so much time talking about subsystem codes is because the first example of a flow K code was really, I think, born out of considering, how we could get logical qubits out of a subsystem code that actually has no space for a logical qubit at all, right? And so the particular model that's, I think, historically several people tried to get logical qubits out of is this Kitaev honeycomb model. And Kitaev initially explored this model for various reasons. It's an example of a frustrated system that is remarkably exactly solvable. In fact, this thing can be mapped to a model of free fermions and so forth. So it's a very interesting thing to look at purely from the condensed matter perspective. The way that it's defined is it's on a hexagonal lattice on a torus, right? So basically, like, the vertical direction loops in on itself, and the horizontal direction also loops in on itself. And for each of these edges in the hexagon, we have, kind of the leftwards, upward slanting edges. We define those as the X edges. The one slanting this way is the Y edges, and the one slanting like this, the Z edges. And so basically the idea is that for each of those edges, you define like two-body XX checks, YY checks, and ZZ checks. right? And you can do this for various values of the couplings in general, but for our case, we'll set all these couplings to be the same. So the idea is that, like, what if you imagined the group, the non-abelian group generated by all those two-body checks as a gauge group in its own right, right? And so, okay, so let's do a little bit of math for this gauge group. We say that, like, okay, there's one check per edge. Now, each edge, each plaquette operator, each hexagonal plaquette has 6 edges. So the number of edges is naively like, or okay, so the number of, the dimensionality of the gauge group, which is defined as the number of independent generators in that gauge group, you can naively associate that with the number of edges, which you can say is like, okay, 6 times the number of plaquettes because there are 6 edges in a plaquette, but then every edge is shared by 2 plaquettes. And so that, you divide out by this factor of 2 and you're left with 3 times the number of plaquettes. But there is a constraint, which is that the product of all checks and all vertices, if you multiply those together, then you'll end up with, product of X, Y, and Z on basically all the vertices. And that's basically the identity. And so that's a constraint that removes 1 degree of freedom. And so you're left with 3 times the number of plaquettes minus 1 as the total dimensionality. Okay, so since this is a gauge group, we'd like to identify what the stabilizer subgroup of this thing is. And the stabilizer subgroup is given by A, the product of checks around the edges of a hexagonal plaquette. So in other words, if I look at, one of these hexagonal plaquettes and I just multiply this XX check with this ZZ check with this YY check, etc., and just go around the loop, I'll end up with an operator that looks something like this. So it's like, X, Y, Z, X, Y, Z. And so that particular product of checks, you can convince yourself that that will commute with every, two-body check defined in this gauge group. It's going to, commute with this X check and this Z check and this Y check, etc., right? So these form a commuting subgroup of the gauge group. Those are part of your stabilizer. But there's also 2 other operators that are defined on the torus. And those are basically given by like your non-trivial loops. So I said that we're putting this hexagonal lattice on a torus, right? So as you go around that torus, if you just trace a path, right, like that, something like this that goes vertically, and you just keep on multiplying the checks that you see along the edges that you've traversed, that too will commute with every check that's in the gauge group. But it's not part of the gauge. Well, so sorry, that is part of the gauge group. Importantly, that is part of the gauge group. And then also similarly, if you traverse a horizontal path across the entire lattice, which will then, repeat itself and come back here again. That again, if you take the product of all of those checks along that path, it will form an operator that commutes with every other check in the gauge group. So those are 2 homologically non-trivial loop operators. They are part of your stabilizers. And once again, like, you have this constraint that the product of all the plaquettes has to be proportional to the identity. That removes 1 degree of freedom. So you end up with this many, independent degrees of freedom in the stabilizer subgroup.
Hey, so quick question if I can.
Yeah, of course.
Is the condition that the product of all plaquettes proportional to identity, is that something we're imposing, or is that just a byproduct of how we've laid out the...
It just naturally comes about. Yeah.
Okay. Okay.
Yeah, exactly. Because I mean, it's basically just saying that, like, if you what I guess, like, I mean, the non-trivial statement is really that if you take this product of all plaquette operators, you'll find that it's actually equal to the product of X times Y times Z on all the vertices, right? And that's proportional to like the identity. And so what I mean, the identity is some fixed matrix or some fixed operator, right? And so that means that if you know what like P minus 1 of these plaquette operators are, you've fixed what that remaining last, pth plaquette operator is.
Yeah,
so
absolutely makes sense. Just to clarify.
Yep. Okay, so the punchline of all of this is that you can compute the number of gauge qubits. You'll find that it's this number. And so remember that we said that in subsystem codes, your entire Hilbert space, your entire number of physical qubits, once you transform into this virtual qubit basis, you'll find that there's a certain number of stabilizer qubits, a certain number of gauge qubits, and then whatever remains is like precisely your logical qubits. But here, just because of, purely by the identification of the gauge group itself, you find that like the way that it splits up is that you have a certain number of stabilizer qubits, but then your remaining, gauge degrees of freedom, they basically eat up all the remaining degrees of freedom there are. And so there is no space for a logical qubit when you view this thing as a subsystem code. And so Hastings and Ha came up with this remarkable technique where they said, well, let's say that you just, carry out this like very particular measurement schedule of the check operators, right? And so this hexagonal lattice, and the way they define the measurement schedule is like, they said, okay, this hexagonal lattice that we just saw, which has these, X and Y and Z type checks, right? Or edge operators. This is a 3-colorable lattice, right? So let me just, color or number each of the hexagonal plaquettes with 0, 1, and 2, such that like no neighboring no neighboring plaquettes share the same number. And then moreover, I will also label the edges as those that are connecting, so for example, if an edge connects like a type 0 plaquette with a type 0 plaquette, then this I define as a type 0 edge, right? And likewise, this is a type 1 edge because it connects to type 1 plaquettes and so forth. And this is a type 2 edge. So what they said is that the measurement schedule is just measure all the type 0 checks, followed by measuring all the type 1 checks, followed by measuring all the type 2 checks. And their claim is that if you do things in that manner, then remarkably, those two loop operators that we just talked about, right? Like, which was like the product of all those checks along the vertical direction and the product of all the checks along the horizontal direction, those never get measured. And so because they never get measured, they always remain outside of your instantaneous stabilizer space. And so those actually form your logical degrees of freedom. And because there are two of those, you get precisely 2 dynamical logical qubits in this case. And I won't go, in the interest of time, I won't go through too many of these details, but please, press me on giving you those details if needed. But the idea is that, like, I'll mention that this was the first example of a Floquet code, and it was essentially accomplished by promoting things inside of the gauge group to logical operators. So basically we're saying that, like, these things, even though they're part of the gauge group, they will never actually get measured if you follow this particular measurement sequence. We already said that, like, what those 2 logical operators are, but those are Z1 and Z2 operators, and correspondingly the X operators, it actually turns out it's a little bit tricky to construct in the case of these hexagonal Floquet codes. And they're generically given by thinking about, by thinking in terms of these like embedded toric codes. So we said like how we're measuring, these 2-body check operators. And the idea is roughly that once you fix the value of this like 2-body check operator, then the resultant code you have, like, you could think of that, like, that fixed degree of freedom as essentially being just a single qubit, right? So for example, if you have 2 qubits, but you fix the value of ZZ to be, say, +1, then the resultant space you're in is like spanned by 0, 0, and 1, 1, right? And that's just 2 vectors, which is equivalent to like a single qubit, right? And I guess more abstractly, you could think of it as like, the resultant Floquet code at any one instant is a code concatenation of the 2-qubit repetition code with a hexagonal surface code or toric code in this case. And in the language of toric codes, like we have this notion of electric and magnetic operators, which is essentially the idea that the magnetic operators are those that traverse the plaquettes, like in this way. So this, like, the stuff drawn in teal, I guess, over here is the embedded toric code. And the magnetic operators are those that basically, if you terminate them, they will flip a plaquette operator. So in the case of toric codes, you have plaquette stabilizers as well as vertex stabilizers. But if you terminate a magnetic operator, then it will flip basically, the plaquette operators on its boundary. And in the case of these electric operators, you'll flip vertex operators at its boundaries. So that's how you have to construct those X operators, is by moving to this embedded toric code picture, and it's kind of complicated. So this is one of the reasons why we were like, okay, is it possible to do things differently? Let me just quickly mention that the way that you actually evolve your dynamical code space is given ultimately by very simple rules. And the idea is that, like, if you measure, so say that you're in some stabilizer code space and you measure some operator P, if it's already in the stabilizer, then you're just measuring something that's in the stabilizer again, and that measurement is deterministic and reveals whatever value that operator has. If it's not in the stabilizer, but it commutes with every element of the stabilizer, then it's just going to take some value. I mean, it's going to take some random value upon measurement, and then that operator is going to be added to the stabilizer. This last case is what makes things interesting, is where if the thing that you measure does not commute with some, with one or more elements of the current stabilizer group. And in that case, what you do is, like, you rewrite your stabilizer group in terms of like one element that anti-commutes with this thing. And then everything else you just multiply by that same anti-commuting element. And so in that case, you replace that single anti-commuting element with the thing that you just measured, and everything else is now part of like a commuting subgroup of your current stabilizer. So your stabilizer actually gets updated to something that was previously as like, S naught, where S naught is like the part of the stabilizer that commutes with P, as well as Q, where this Q is something that anti-commutes with P now. This Q part gets replaced with P. So this is how your code space actually kind of changes, right? And at any one point, depending on what you measure, in the previous round, it could have been something else, and now it's something else, right? Okay. So in our case, like I said, like, we wanted to see if we could construct a Floki code on a square lattice. Ever since that first example of Hastings and Ha, many examples came up, but most of, if not all of them, involved a trivalent, tricolorable, and usually hexagonal lattice. For the purposes of, like, perhaps one day actually putting this on an experiment, it would be nice if we could put it on something much more simple, like a square lattice architecture. As we just discussed briefly, like the description of those Floki codes is also kind of complicated, because you have to discuss like non-trivial automorphisms between electric and magnetic operators, and that can also complicate things when you try to introduce a boundary. So, I mean, the example that I just discussed involved a torus, but as soon as you try to impose a boundary, you'll find that, like, it's not actually straightforward, that things are actually quite complicated because of this time aspect of, these dynamical or Floki codes. In the case of the Bacon-Shor Flokification, things are nicer because the Bacon-Shor code actually comes naturally equipped with a boundary. So you don't have to put it on a torus. You could if you wanted to, but you don't have to. And you don't have to talk about embedded toric codes or electric and magnetic operators. You really just can use this virtual qubit description if you just identify what the correct virtual qubit operators are once and for all. And interestingly enough, you can add as many qubits as the lattice size and the target distance allows. So in the remaining time, I will just talk about the Floki Bacon-Shor code construction. And Just as a quick review, the Bacon-Shor code is a subsystem code whose gauge group is generated by all these nearest neighbor two-body checks. The XX checks are drawn in red, they're horizontal. The ZZ checks are drawn in blue, they're vertical. There are two types of stabilizers, right? There's the X-type stabilizers, which is given by the product of all X checks along a column of square plaquettes. And there's the Z-type stabilizers, which are given by the product of all Z checks along a row of square plaquettes. And this is a nice sort of description of the virtual qubit operators. It's, again, not a unique choice of virtual qubit operators, but it's a particularly useful one for flokifying the Bacon-Shor code. And the idea is that, again, if you do the counting for the gauge group of the Bacon-Shor code, you'll find that the number of gauge qubits you actually end up with is the same as the number of square plaquettes on the actual physical lattice. So in other words, I can associate each one of these squares with a gauge qubit. And because I can do that, now I can also say something about what the X and Z operators of those gauge qubits are. So remember that we already said what the stabilizers are, right? So we said that the stabilizers are given by these Z-type stabilizers that run horizontally, and these X-type stabilizers which run vertically. And again, I can think of these as like the logical Z operators of these Z stabilizers. Oh, sorry, of these stabilizer qubits. And correspondingly, they will also have some X operators, which anti-commute with these Z operators, right? We also noted what the logical, the logical operators are for the Bacon-Shor qubit. There's just one of those, right? And that's just given by like the string of X's and the string of Z's. And now finally, for the case of these gauge qubits, I can similarly define what their logical Z and X operators are. If I'm talking about this particular gauge qubit and this square plaquette, then the Z operator for this gauge qubit is just given by the product of Z operators towards the right, and its X operator is just given by the product of X operators above it. And that's all the virtual qubit operators you need, essentially. So, okay, so now let's take another look at the Bacon-Shor code, this time from a Floquet perspective, right? The way that you would actually carry out the stabilizer measurements, like we said, is like by measuring the X checks followed by measuring the Z checks, right? Once you measure the X checks, then you can infer what the values of the X stabilizers are, right? So for example, I measured all these X checks, and then, I'm going to follow that by all the Z checks and, and therefore infer what the values of the Z stabilizers are. Now, from a Floquet perspective, what this is saying is that I'm basically moving between two different instantaneous stabilizer groups, which in this case, I can really interpret as a gauge fixing, two different gauge fixes of the Bacon-Shor code. And the way that I describe these gauge fixes is by painting the square plaquettes either red or blue, right? If I paint it red, I'm basically saying that I've fixed the X operator of this particular gauge qubit. Remember that gauge qubits are in one-to-one correspondence with the square plaquettes, right? So by painting this square red, I'm saying I'm fixing the X operator of this square plaquette or this gauge qubit. And by painting it blue, I'm saying I've fixed the value of its Z operator. And you can see why this happens, right? Because if I just look at some gauge qubit over here, because I have measured, so this is the same as this square plaquette, because I have measured this check and this check and this check, basically I have fixed what their products are as well, trivially, right? And that product is exactly the X operator of this gauge qubit. So I have measured what that X operator is, and therefore I have fixed the value of that X operator. So it's these two gauge fixings that I'm, evolving periodically driving through, right? So now if I wanted to make space for an additional logical qubit, I have to introduce some kind of a gauge defect. Or in other words, I have to sort of not fix one of these gauge degrees of freedom, right? And so in general, it's kind of hard to introduce a static gauge defect in the Bacon-Shor code. if you also wanted to maintain the property that you want to measure all the stabilizers of the Bacon-Shor code, but you can do so in a dynamical fashion. And that's exactly what this proposed measurement scheme does. So the idea is that you skip, so I'm gonna label these important cells A, B, C, D. And the important point is that we skip all the measurements of all the X checks in this particular column. And then so the measurement of all the X checks is split up into rounds 1 and 3, where in this round we measure all the X checks except those occurring along this column, with the exception of just this particular edge AD. And over here, then we basically repeat that pattern, except this is the defect column in this case. And the point is that we're sort of splitting up the measurement of the X stabilizers into 2 different rounds. And in this manner, we can temporarily maintain a gauge defect over here, but eventually move that gauge defect sort of 1 column to the right, and then we can measure the X stabilizer in this particular column. And we do something similar for the Z stabilizers as well. And this particular, so it's I guess I'd have to go through a long history of why this thing occurs, but basically, we're not really introducing a gauge defect in a single cell or single gauge qubit, but rather the way that we introduce the gauge defect is through a product of those gauge qubits. So in other words, your pairs of logical operators evolve in this particular manner. So the logical Z operator, for instance, is given by the product of the Z operators of gauge qubits A and D, right? You can take the logical X operator to just be the X operator of this gauge qubit A. But then, the idea is that in order for logical information to be preserved across these different rounds, one thing that you have to make sure is that there's some representative of the X operator in this particular stabilizer code. So now, each of these 4 rounds, really, you could think of them as stabilizer codes in their own right, right? And the logical operators of any stabilizer code is given by, some representative of the logical operator, in this case, XA, times any member of the stabilizer group. So the idea is that some representative of the logical operator over here has to be a representative of the logical operator over here. In other words, a stabilizer element in round 1 times this X operator has to equal a stabilizer element in round 2 times this logical operator. And in this case, it's pretty simple, right? So XA, I could just multiply this by XB, right? And just get XA, XB in the next round. ZAZD is also simple enough, right? So for example, I have fixed this product, ZAZB. So I can multiply this by that product, and I can also multiply by ZD, and that will get me from ZAZD to ZB, etc. So logical information is preserved. These logical operators connect in the required way. And at every one point, I have maintained this kind of a single gauge defect, and the idea is that it's important that we don't have any X operators along this column, because as you can see that with this measurement schedule, in terms of gauge fixings, the only things that appear above this column are just fixed Z operators. If there was any single X operator over here, it would actually reduce the distance. But without those extra X operators, essentially, basically, because this distance from the edge of the lattice down to where this gauge qubit A is, it's roughly D over 2. But because that's D over too many edges, I can, and an edge contains 2 qubits, I would multiply that number by 2. And so I'm roughly getting the same distance as the original Bacon-Shor code, which is, again, just D. Okay, I didn't realize I was taking up so much time, so let me just power through the rest of the slides. But the thing that I want to get across is that this could also then be generalized to the case of multiple dynamical qubits, right? So you don't just have to limit yourself to one. In general, like you could introduce, like, let's say if you have, in this case, like I'm introducing 9 more dynamical qubits, and the idea is that you just place them strategically such that any one of these gauge defects is roughly d over, some number. In this case, it's 3. It's roughly d over 3 away from, any edge or from each other's. Um, and then if you can do that, then like, you'll get 3 by 3 many logical qubits as well. And the price that you have to pay is that for introducing k many dynamical qubits in this way, your code distance shrinks from d to d over square root k, which isn't that bad, of a shrinkage, in my opinion. Okay, so a few words about error detection and correction in the usual Bacon-Shor code. The idea is that, as we saw earlier, like if there's a single qubit X error on the topmost row, those are all equivalent to one another. And in fact, any even number of errors on any row, any even number of X errors on any row is actually part of the gauge group. So this is equivalent to like having no errors at all. In the second row, we have 3 single qubit X errors, but that again is equivalent to just a single qubit X error. And conventionally, like you can choose like whichever qubit you want to place it on. I'm just choosing the convention in which like I'm just going to say all the X errors ever happen on the leftmost column, right? So you can do this kind of trick in the case of the Bacon-Shor code. And you're measuring the Z stabilizers, which is going to pick up like, this pattern of X errors. And, this particular pattern will always come in either pairs or just single isolated, stabilizer syndromes. And so you can use something like minimum weight perfect matching for something like this. In the case of the Flow-K Bacon-Shor code, things are a little bit more complicated because you now have this kind of error in equivalence because of the fact that you have this kind of blue domain wall, this domain wall of like Z operators in the middle. So what that means is that these errors that live on the left-hand side cannot propagate to the right-hand side because of the presence of this domain wall. And so they're inequivalent. And so, if you have an even number of errors on the right side of this blue domain wall, then that's still equivalent to having no errors whatsoever. And likewise, if you have like, these 2 errors on the left side, that's again equivalent to having no errors. But then if you had like errors, 1 error on the left-hand side and 1 error on the right-hand side, that actually is an error, right? So this is, something that you have to be mindful of. And the other thing is that so previously we only ever flipped like either an independent error only ever flipped either a single qubit a single stabilizer or 2 stabilizers. In this case, we can get something much more complicated. And to be more precise, like, let's say if you have a single qubit X error on the left-hand side of this domain wall, it's going to flip these 2 stabilizers. A similar X qubit error on the right side of this domain wall, it's going to flip 4 of these stabilizers. So 2 of the stabilizers coming from the Bacon-Shor parent subsystem code, but also these Z-type stabilizers. So remember that, these Z operators of these gauge qubits, these were, I guess I'll have to go back a few slides to really show you what I mean, but basically they get measured in this round, right? But they persist across this round, and then they get measured again in this round. And so they can serve as stabilizers that can detect and correct for any X errors that occur between this round and this round. And likewise, over here, then I measured like these Z-type stabilizers, and these persist between this round and then this round where they're measured again, and they could be used as stabilizer checks. Okay, so those are examples of like transient stabilizers. And so to finally wrap, I should say something about self-correcting errors as well, because, I mentioned these pairs of errors now coming in as things that can that are now errors that previously were not errors in the Bacon-Shor code. But so suppose that this kind of 2 qubit error pattern occurred in this particular round, or between these two measurement rounds. In this particular round, they are going to flip these two transient stabilizers. But the idea is that in the very next round, these two things become actually part of the part of the instantaneous stabilizer group. So whether you actually apply a correction or not doesn't matter, because it's actually just going to get applied anyway. So it's and this happens for all these these 2 qubit X operators over here, as well as like 2 qubit Z operators over here, etc. So in conclusion, we're basically saying that flow gate codes could be constructed from subsystem codes by introducing gauge defects, that certain errors could be corrected purely by the measurement schedule, but that because you can flip more than 2 stabilizers now, like an independent error or fault can flip more than just 2 stabilizers. You might need something beyond minimum weight perfect matching or union finder type techniques for decoding. These are also something that are, I think, relevant for LDPC codes. So there's a lot of work being done in that direction. Unfortunately, like the parent Bacon-Shor code, the Floquet Bacon-Shor family of codes does not possess a threshold, and that's coming from the fact that as you increase the lattice size and therefore the distance, you're also increasing the size of the stabilizers. And so for any fixed value for any of the physical error probability, it becomes more and more likely that you're going to get some measurement error in the stabilizer values. A few open questions. So, as we were kind of like in the process of thinking about all of this, Craig Gidney and Dave Bacon released this paper where they introduced a threshold to the Bacon-Shor code purely by they're saying deleting gates from its circuit, but basically what they're saying is like skipping the measurements of certain check operators, which is what we're doing as well. So in their case, they somehow managed to introduce the threshold. In our case, we managed to introduce more logical qubits. So is there a way to combine both those techniques together and get both of those things? Not immediately clear to me if that's possible, but I leave that as an open question. And secondly, we said that like we have multiple dynamical qubits, so can we do multi-qubit logical gates between them? It certainly seems plausible, because a lot of what we're doing is, to me at least, pretty strongly reminiscent of techniques such as lattice surgery and so forth. So it's conceivable, but one has to really dig in. And so these are some of the things that I'm particularly keen on thinking more about. So if this sounds like something you'd be interested in, please give me a shout, and I'd love to chat more. And I've already taken up like I've already gone extra. So thanks for listening. That's my contact info. I'm more readily available on my USRA email address, but please feel free to also reach out to me on my NASA email. And thanks again for having me, and thanks for listening.
And thanks so much. Thanks so much, Sohaib. This is really great. We have a quick minute for questions. I'll stop the recording so people can ask freely, but just say thanks again. This was really interesting work and very clearly presented, and all well on vacation. So that's very much appreciated.
Absolutely. No, thanks for having me again.